Today I will start on continuous random variables, but before that, I noted that there was some minor mathematical grammar error while I was writing something down. Just want to point it out. Maybe you all have noticed and already you understand it, but nevertheless, we had some problem in which we had this random variable expectation of, yeah, we had this s given n, which is actually psi of n, and n assumed values maybe 1 2 3. I don't recall, maybe it is 0 1 2 3 whatever, and I think 1 2 3. And I was trying to tell you, we had computed e of s given n equals n. That turned out to be some number a times n. I don't remember whether what the notation was, but it's something dependent on n, and the dependence is something very simple. And from this, I concluded that psi of n, this is all okay, absolutely no problem, a times n. And while explaining why this is so, I seemed to have written psi n of n. This is not quite correct. I should have written omega here. This is all I wanted to say. So it should have been omega here by, for some, not, I was not paying attention. So once this is this, what is this? So this is a function of, mind you, the psi of n is just nothing but you have some omega to real numbers, that's your n, and then psi is some function which depends on, actually here this is natural numbers, and if it's not a natural number then it is 0. That's the understanding, and this maps to else. So so the psi of round bracket n is just a composition, therefore I should take a omega from here and then compute it, and that's all that I wanted to say. So this is same thing as by definition n of omega, and n of omega is some number. So let n of omega is equal to, this is just a notation, is equal to n, then this is psi of n. Okay, so it is not psi n of n, but psi of n. And now you can compute it. So psi of n, so psi of n is exactly this expectation of. Rest of the things are all okay. So it's just that I should have written omega here and I wrote n, which is not, which is absurd. So n equals n. Yeah, okay, so that's it. I wanted to point out, these simple errors. I know for myself it is simple typographical type of thing, but for you people who learn it the first time, it could be confusing. So it's my bounden duty to explain to you what exactly was wrong with that argument. Anyway, so uh, yeah, this is about time. So continuous. We have seen this before, but nevertheless, continuous random variables. Hmm. So, uh, so it's the definition which is somewhat okay. Let me say this. So suppose that x is a random variable, whose distribution function is given by f of x is equal to integral minus infinity to x ft dt, where, yeah, what is f? So f ft or f is a function from here to here, 0 to infinity. Mind you, you should not write 0 to 1. You should allow it to take maybe large values. Yeah. Which is integrable. So this is a bit difficult to explain at this stage. And you may think that this is so a function for which this exists. Okay, that's one way to say it, but that's not saying much. Mhm. Yeah, so this is the, so in general, so suppose you have, so suppose, so you have a notion of this measure, we just cannot postpone this discussion for too long, but at the same time, it's very, yeah, it's an involved kind of definition, so I cannot spend too much time on this. You will learn this more appropriately in your analysis 3, okay, or maybe analysis 1, I don't know, okay. So in your analysis course, you will learn this. So suppose you have a function from here to here, okay. So first of all, uh, yeah. So let me say one thing here. So here, so examples, and this is all that we need to worry about. You don't need to worry about too many other things. So example, f is continuous, uh, but continuous, uh, and yet this integral uh, continuous, and it should make sense to write this. It's not enough if it is okay. So continuous, monotone. Examples of this, which have finite minus infinity to infinity. So already I am assuming that the range is between 0 to infinity. So I should put this line over here, ftdt. Of course, this is which have finite this, and if it is going to be, so in fact it's going to be this finite, and in fact is equal to 1. May as well write that. So instead of saying this, so this is an improper integral which continuous, non-negative valued, or monotone, non-negative valued, and then you can make sense of this as a Riemann integral, okay, or Riemann's, yeah, but yeah, so this will require, even if it is a monotone, I don't want to say, yeah, this is a bit complicated to say. With finitely many jump discontinuities, for example, then you know how to handle this. So let me not elaborate on this, but I will say something about. So the problem is in making sense of this integral. Okay, usual. Yeah. Yeah, so the notion of integrability needs to be explained very carefully, and in order to say that, that will take a long time. At the moment, maybe I don't concentrate on that. First of all, um, let us look at this following situation. I want to say something here, but in order to say that, I need to say something else. Uh, yeah. So, what type of sets? What are the sets? What are the subsets B in real numbers for which it is meaningful to ask, meaningful to ask for probability, okay, for probability that X belongs to B. See, if X was discrete, then this issue doesn't arise at all. We understand it completely. Okay? But if when X is not discrete, and in fact it's given by this, okay, then what can we say about? So what are the sets for which this makes sense? Okay, I want to say that. I want to explain that. This is a very important notion. First of all, let us start off with the following thing. Did I write that? Okay, so recall that this is same thing as probability of x less than or equal to x. Okay, that clear? Yeah. So that's by definition of the distribution function of x. So definitely you can talk about mm, probability of a less than x less than or equal to b. Okay, this will be integral a to b. This makes sense. So a to b ft dt. And we will see in a moment that actually this is same thing as probability of. So at the moment I'll just take this for granted, but I will prove this in a moment. So this is also equal to this. So in other words, uh, in your collection, you can allow, you may allow the, so B to be a closed interval, B to be an interval, any interval. What type of interval? So A, B, or A, B, you can put open or close or whatever. And so what does this mean, therefore? So this means that this, first of all, this set, yeah, you are demanding that this, so there is a simple answer to this. This happens, this is meaningful if and only if, so this is equivalent to asking omega in capital omega such that x of omega is in B. Okay. So this must be in script F. Okay. So the moment that is there, so this is like saying, so this is like saying, so you think of x as a function, x inverse of these sets, a comma b, etc., or in F, and open interval and so on and so forth. I'm not writing all those things, so etc. Okay, but the moment that happens, you also know that your F is closed under countable union, uh, complementation, countable intersection, and so on. Okay, so this means that we may allow, uh, we may allow B to be in the sigma algebra, in the sigma field generated by by generated by what? The intervals, by open by intervals in R. Okay, so mind you, B is a subset of R. So this is called the Borel sigma algebra, Borel sigma field. Okay, so this is an important notion. And first of all, so we require F from R to R to be such that F inverse of B uh, is again in Borel, in the Borel sigma algebra. Actually, a little more sigma, Borel sigma field. Okay, in fact, we may allow. So this is what is just so you can say a little more because anyway you are going to consider uh, closure this. Okay, let us just be content with that. You can slightly say, you can be instead of requiring this, you just say that. So, let me say it here. We will say that F is measurable, or Lebesgue measurable. If F inverse of B is Lebesgue measurable, is in the completion of the Borel sigma. So this is completion Borel sigma field. You didn't have to look at completion so far, but now you have to. So this is the basic thing. So this is saying initially I said we require, but so we don't really require it. Yeah, this is enough if so you can make sense of Lebesgue integration when F is one can make sense of the symbol integral over R ft dt, or just ft dt if F is Lebesgue integrable, Lebesgue measurable. But you say that it is we say that F is, let me write in bracket, Lebesgue integrable. So integrability will always mean in the sense of Lebesgue integrable. If it is Lebesgue measurable, and if so, I have not told you what is the value of this or what it is. It is going to be some number in real numbers, but extended real numbers, plus minus infinity also is allowed here. But here you just look at this mod ft dt over R. This must be finite. So we say that this is integrable if this is the case. And when that happens, okay, now And so this it is in this sense that you want to make sense of the first in this definition here. Okay, so this is same thing as saying over the integral over the interval minus infinity to x ft dt. You just compute it, whatever be the meaning. And the meaning is the most natural one, and I will not go into it. It just coincides with the usual notion that we know when ft, for example. So, so okay, the definition of this itself, in fact, is given in terms of integration over of step functions, and for step functions, you know what it is. So, if so, examples. These are most important examples. First of all, examples. So f is equal to some finite linear combination ai some ak. Uh, yeah, first of all, do it for intervals. Okay, okay. Change it here. So step function, and they are just indicator functions. So I write here I, and here you write ai, ak, bk. All right. So this is indicator function, and only finitely many. K goes from 1 up to n. In this case, so these are all integrable, that's obvious. And what is the value of this integration over r ft whatever? Yeah, f ft dt. By definition, this is equal to summation lambda k bk minus ak, length of the interval. Okay, that's it. So, so for step functions, it's exactly as expected. In general, any function which is measurable can be sort of approximated by means of these things, and then you pass the limit. There is a lot of things to say, and I skip all that. So, so for example, from this, the definition itself, it will follow that if you have a continuous function or a monotone function, which is vanishing outside a compact interval, then they are all integrable over the whole thing. Mind you, first of all, here you take absolute value and then try to do this. So anyway, I think said enough about these notions. You will learn more properly in greater detail in an analysis course. At the moment, I am saying all these things for two reasons. Okay, first of all, f need not even be continuous. F need not even be monotone. Things can be more complicated than that. And yeah, in our special context, we want not only that. Yeah, so in our special context, this taking mod f is redundant because it already takes values only in non-negative reals. And when you integrate it over the whole thing, that must be giving you actually value equal to 1. Okay, so and one last thing, so just in case if somebody is curious and so on, want to learn more about these things ahead of time. So the notation for integrable functions is L1 of R. Okay, and of course we are looking at very special type of L1 functions in L1. But I wanted to say one other thing, not just say the notation. In this theory, you identify two functions f and g. If the difference f minus g, okay, uh, vanishes, yeah, f minus g vanishes outside a set of measure 0, set of measure 0. Okay, so that's the main thing. So this is elements of here, they are not actual functions, they are equivalence classes of functions. But mm, when we do a specific integration, of course, we will work with specific functions. Okay, so I have said enough about these things. The notion of this. So the main difference between continuous and discrete is that, yeah, so uh, you cannot, yeah, you need to restrict your f suitably so that it makes sense to talk about probability that x belongs to b. So the since this b, you want to allow it to be arbitrary element of that Borel sigma algebra, Borel sigma field. Okay, b is allowed to be in Borel sigma field. All right. Uh, yeah, I think that's the main thing. Now let us prove something that I mentioned earlier. So lemma. Yeah. So suppose that so before I say this definition, the function, this is an important definition. The function uh, f of t uh, is called the density of capital X. Okay. So this ft, as in this original definition here, yeah. So this definition, that ft corresponds to this ft, and ft is called density. Actually, one should call ft dt as a density. So there's a slight abuse of language here. So ft, we call this the density. Okay, suppose that ft is the density function. Here also say the word the density function doesn't make any sense, because it's not just one single function. I can change the values of f at finitely many points, and or maybe on a set of measure 0, whatever it is. So I can still make sense of that integration and so on. So but we just use this is the density function, density function of a random variable, of a continuous random variable capital X. Then um, of course, integral f to dt minus infinity to infinity ft dt is equal to 1, and probability of x equals x is equal to 0. So this is number 1 or A, B. I don't remember what C is, but probably something very simple. Yeah, I just need to look at this. Just a second. So sorry. Just a minute. I need to see what the third thing. Okay. So this is something I already wrote. Not to worry. So probability of a less than or equal to x less than or equal to b is equal to integral a to b ft dt. Okay, this is something that I have already discussed. This is something uh, we know already, because this is the probability of the whole space. Um, okay, and what about this one? This one requires some explanation. Okay, Hmm. So, hmm. Yeah, so the thing is integral, probability of x equals x is equal to, I can say like this, uh, limit h think increases to 0, probability of x is less than or equal to uh, x minus h, a minus, sorry. Yeah, okay. So I could have written here, okay, let me write here x minus h. Mhm. So this by the properties of integrals, limit h goes to 0. Okay, well, from the definition or property and property x minus h to x ft dt. Mm. But this is actually, this goes to 0 as h goes to 0, as h goes to 0 for integrable functions. Okay. Why so? See, if the function is integrable, then it is sort of in a, it is essentially bounded, you know. But this interval has length h. So one has to talk about essentially bounded, you know. I mean, so that is an important thing because otherwise, see, what it means is that, see, f need not be bounded. For example, it can take integer values at integer points, and that would make f unbounded. Or it can take integer values even within the interval 0 to 1. At points like, say, specific points 1 by n. I mean, it's a vague equivalence class, right? So at 1 by n, it can take value n, and at other points, it takes a value 0, suppose. Okay, and we are only concerned about in this interval. Then, near 0, it is not bounded. So even near a point, this function can be unbounded. But the place where it becomes unbounded has to be a small set. Otherwise, if it's a large set in the sense that it has a positive measure or something, then that would go to, then the integral wouldn't exist. Integral will become unbounded. So for integrable functions, so this is, in fact, if you, so so this is in fact less than or equal to length of the interval, which is just h times. So limit, there's a limit. So limit h goes to 0. Okay, through negative values. So sometimes I write like this, but better to write like this. Yeah. So this is h. Okay. So let me write here h. Why did I write that? Here I wrote h increases to 0. I think maybe I should write here decreases to 0. Better to write like that. Because in my mind, h is positive, 0 minus, 0 plus, through positive values. Anyway, so this is h times 1. Mm. So in a in a small interval, okay, in that interval. So I'm not saying ft is bounded by 1, but in a small interval, this will be bounded by 1. It's essentially bounded. So this goes to 0. as h goes to 0 plus. Okay, so but it's intuitively clear, right? You cannot have at a particular point. See, it's like saying that no matter how small. See this uh, probability that capital X equals X is taking specific value would imply that you have a so at that value X naught or whatever you have a point mass. Okay, when you have point mass, no matter what interval, size of the interval you choose around it, okay, the function, you cannot, so if you evaluate this will not, it will not go to zero. So this is a problem. So you cannot have a point mass. So only when you have a point mass, can you expect that probability of x equals x to be something not equal to 0. Okay, so I have said enough about this. So this is a subtle point where, and it is worth emphasizing. And I will do one example just to emphasize that F can takes. We have done this type of examples, but let me do this once again. Suppose,
Sir,
yes.
sorry, I have a doubt. Earlier you said something about the completion of a Borel sigma field, but isn't Borel sigma field already complete?
No, Borel sigma. There's a slight difference between Borel measurable sets and you remember. See, you remember we studied this process called completion. See, of course, you take all possible. So you complete it in the sense of getting a sigma field. Okay, so you first of all start with intervals, and then you form countable union, complementation, countable intersection, the complementation, so on and so forth, and you keep on doing this in order to get a sigma field. That is, and the resulting collection is called Borel sigma field. But it may not. It will have. See, the thing is distinction between this the Borel sigma field and Lebesgue measurable set. So a set is measurable if it belongs to Borel sigma field. Um, but you can have a set of measure zero whose subset is not is a Borel is in the Borel sigma field. Okay, so you complete it with respect to that, with by in the sense that you throw in all sets which are subsets of measure zero sets. Okay, so I didn't tell you what is a measure zero set, but what is a measure of an interval? Measure of an interval a to b is b minus a. Okay, so when you do these various processes, for example, rational numbers, it will turn out to have measure zero. Okay, and maybe some uncountable set also. For example, the Cantor one-third set, the standard Cantor one-third set has measure zero. But it may be that when you write subsets of the Cantor set, not all of them are expressible as Borel's. Not all of them are in this collection of Borel sigma field. Okay, so it is completion with respect to that,
So it
and
is
that
the sigma field plus those sets with measure zero.
yes,
Okay. Yeah. Thank
throw in
you.
all that. And of course, not just that. Once you do that, then you have to also take countable union, countable intersection. Another way, to simpler way to say that is you take any set E measure and suppose that you have a set E, F, and then E dash. Okay, and E dash have the same measure. And Borel, of course, you talk about measure only for, to begin with, only for Borel sigma fields. And if F turns out to be like this, F may not be in your Borel sigma field. Throw that in also. Then that is your entire Lebesgue measurable sets. Okay. So that is why Borel measurable sets forms I mean, the Lebesgue measurable, that is much more than just saying Borel measurable, Borel sigma field. Okay, so that's all I wanted to say. All right, so now what you do is this following. Yeah, just I want to give again, once again, an emphasis on this aspect that you can have, suppose ft is equal to say n on for 0 less than or equal to t less than or equal to 1 by n, 0 otherwise, then ft is a density function, is a density function of a random variable. You can take, for example, the uniform example. So you have to say what is omega and so on and so forth, right? So I'm fixing an n here. So example, you take omega to be just the interval 0 to 1 by n, and x, yeah, mm, so x, so okay, so this is the x of t equals t. So this is going from, sorry, x of t, do I want it to be t? Yes, I suppose so. Okay. And now what is the probability that x is less than or equal to t? Okay. This is equal to, uh, yeah, so I haven't told you what is the, this is uh, just, so so this with so I must explain independently what is this probability, on this one. So this is probability uh, of okay, of an interval. So a comma b is equal to n times b minus a. All right. So this is what it is. Now probability that x less than or equal to t is the same thing as probability of, just do this. This is a very trivial problem. I'm doing it just for sake of clarity. I mean, what is this set? This is same thing as 0 to t. And which you know is n times t. No, n times t. But this is same thing as integral 0 to t of what function? So now I should better change the parameter. This function fx dx, because this fx dx is just n, constant function n. Okay. So if you are not able to see it, so here it is. Ft is always n in that interval. Outside of that interval, 0. So you can rewrite it if you like between minus infinity to t fx dx. And this holds. So here to begin with, it is holding good for what? So t less than or equal to 1, 0 less than or equal to t less than or equal to 1. But you check that this is also true. If t exceeds 1 also, no problem, because f has become 0 in that. Okay, so this is just a very simple example. Okay, now I want to already talk about some other related. So what we are going to do is we are going to develop the theory parallel to what we have already done for discrete random variables. And for that reason, I will go a little fast. We will work out specific examples possibly today itself, but for now, I want to talk about independence of random variables. So this is throughout I'm only talking about continuous random variables. Okay, continuous random variables. So suppose x and y are your uh, continuous random variables. Yeah. With density functions. Okay, so yeah, so we say that x and y are independent if probability that x less than or equal to x, y less than or equal to y. So this comma means and, okay? The same thing as probability x less than or equal to x times probability y less than or equal to y. Okay. So in this context, yeah, maybe one should talk about also joint. So I have already talked about joint distribution functions. So recall that uh, so the joint density function of uh, two continuous random variables xy with joint distribution function f xy of x comma y. So what is this? This is by definition probability of x less than or equal to x, y less than or equal to y. Okay. Now what this says is that, so I said this thing joint density function. So I forgot to say what is that function. I write that here, fxy. Fx comma y of x comma y is such that, so this is such that corresponds to fxy. So fxy is such that fxy of x comma y is equal to integral minus infinity to y, integral minus infinity to x. So f x y s comma t ds dt. Okay. And the order in which you integrate does not matter, and that is justified by what is called Fubini's theorem in general. Let us not go into that. So this is also the same thing. Okay, is equal to minus infinity to y, x minus infinity to y, fxy of s comma t dt ds. And what this one is saying is that, so let x comma y, yeah, fx of x, fy of y, fy of y be the density functions of x comma y, then so here you are saying that, yeah, probability that this is less than or equal to this, and this is less than or equal to this. Product is a product of these things. So this is same thing as, so so this is equal to, yeah, okay, product x less than or equal to x times y, p of y less than or equal to y is equal to um, integral minus infinity to x fx of x integral minus infinity to y fy of y dx dy. So here it is dx, here it is dy. Okay, and I can rewrite it in this particular form. So write it together, minus infinity to x minus infinity y, doesn't matter, fx of y dy. And so if you look at the difference of the two, then in fact, yeah, these are positive functions. So and this is true for every x and every y. That is also required. Okay, it's true for every x and every y. I probably said that at the beginning. So, so this is true for every x and every y. Okay. So again, you just notice that. So if you just so in this, I will not prove this because in this case, fxy of x comma y is equal to fxx times fyy. Okay. So this is an important thing. So the density function of the joint distribution function, same thing as product of these individual things. In fact, if you just stare at these equations, you can just look at the difference. Fxy and fxs. Sorry, here I should have written s and t. No, that's only correct. I should write s here and t here. So this is s going from minus infinity to x and so on and so forth. You see, if you look at this integration, I just remark. So you look at this fxy x comma y minus fs fxx. Sorry, I should have written s and t. These things happen. So s comma t as fyt here, right here, yeah, ds dt, doesn't matter in which order you integrate it. So here s, because you say that this is valid from where to where, all, for any x and any y and so on. So here you can actually write a rectangle, and then also there also it will be 0 for any rectangle R. R is a rectangle where, so is a rectangle s comma t, and you can just write a less than or equal to s less than or equal to b, c less than or equal to t less than or equal to d. This you can prove from the fact that this previous equation is valid, that, okay, for all possible s and t. So I'm just giving something to justify this. Again, you see, so again, you cannot say that this is actually equal to 0. Uh, all you can say is that, you see, this is 0 almost always. Okay. if you don't want to think about this almost always business, just work with the continuous functions. So suppose this is equal to 0. This is 0 for all possible rectangles like this. That is all possible A, B, C, D. This is 0. Then if everything involved here are continuous, then this has to be 0. Because somewhere, if this is not equal to 0, say positive, it could be negative also, say positive, then in a small rectangle, it is strictly positive, closed rectangle. And if it's a function which is continuous, then it will attain its maximum, minimum somewhere, which is away from 0. And there you can estimate this integration. It will be area of that integral times the minimum of this, but the minimum is positive. So this would be violated. Okay. So if you are working with f and small f, the density functions themselves to be continuous, these things are easy to do.
Sir,
Yes.
so could you explain some? You said something about minimum right now. I don't think I understand.
Yeah. First of all, the fact that when you have independent the saying, this gives you, so fxy, you have two formulas for fxy, right? This is also fxy, capital fxy. Let us drop the suffixes. So here, anyway, let's write this. So you have two formulas. Uh, yeah, one is this product. So this product, okay, or here integration, but two different distinct product functions. Here you have just one fxy of st. This is the joint density function by definition. Okay. Now the difference of course is 0. And the difference is being 0 for any x and any y says that the difference is 0 when you integrate it on a rectangle which is of this form. That means like it's like a to b, c to d. This is 0 for any value of a, b and any value of c, d. Okay, so that means that my whole concentration is only in a small rectangle like this. So this is a to b, okay, and this is b to c, c to d. Okay, this is AC, whatever, AD. Okay, so now in this rectangle, this is a closed rectangle, and suppose everything here is continuous. So this is a continuous function on a compact set. If you have not studied it, you will study it later. There will have to be a point where it attains minimum. And I'm assuming that, see, if this function is somewhere non-zero, in a small rectangle, it will be non-vanishing, closed rectangle. If it is non-vanishing, it is strictly positive. That's enough for me. I mean, then I can suppose it's so on this rectangle. All I'm saying is so it takes time to write it. So this quantity is bigger than or equal to some epsilon. Therefore, for all st in R. Okay. Therefore, so if I call this integral I, therefore I is bigger than or equal to epsilon times the area of the rectangle. But this is positive. On the other hand, you know that this is 0 always, irrespective of S and T, irrespective of the values A, comma B, C, comma D. Yeah. So that is why this is not possible. Okay. Yeah.
Yes, sir. So
Yeah.
one more thing, sorry, sir, one more thing. You said something's almost zero. I mean, I is almost.
Yeah, so when a function f, I was making all this, I mean, fuss about function being integrable, and integrable functions need not be continuous. You could have artificially changed values at a dozen points, and so the function is no longer continuous. So, in general, always one should remember when you say integrable function, that itself is you are not talking about a function, you are talking about an equivalence class. But yet, you can talk about what is called essentially boundedness or essentially vanishing. You can give meaning almost everywhere. That type of phrases can be given a very precise mathematical meaning. And from that point of view, this is not, you are not going to say it is zero, you're going to say it is almost always zero. Okay? That is where it is not equal to zero, is a set of measure zero, or is something which doesn't contribute anything to the integration. So, therefore, you can identify the two so far as integration is concerned. That's all that is. Okay?
Yes.
So, but you will realize the subtlety of this when you study more carefully all these concepts in your analysis course. Okay. Uh, yeah. Let me, I have about 15 minutes. I will just introduce this concept, but definitely I'll talk about it in the next lecture also. It is better that I introduce it sooner so that when I repeat it, it is reinforced. So suppose that that uh, x is a continuous random variable with density function f of, so fx of x, or sometimes we just simply write fx. Definitely, I'm going to work out problems. Okay, I try to keep a balance, but some lectures are heavily involved in concepts. Anyway, so expectation of x is defined to be most natural one, integral minus infinity to infinity x fx dx. Okay. More generally, so e of x power n is equal to integral minus infinity x power n fx dx. Okay, and it's called the nth moment. Nth moment. So if you recall the discrete case, there you had the same thing except you had summation. Okay, and this yeah, okay, and variance. Yeah, variance of x. Yeah, so just because I define it doesn't mean it exists. So if it exists, always I have to say this. If it exists, so meaning it should be a finite number. No? So whenever it exists, okay. Variance of this is by definition e of x square minus e of x the whole square. And so, and we have this lemma exactly as in the case of, so let y is equal to g of x. Okay. Where g is a suitable function. Then expectation of y is equal to minus infinity gx fx dx. Okay. All right, I will talk about these things more about expectations and so on. Let us do some very specific problems. and yeah, do some exercises and so on. Okay, I want to do some examples of continuous random variables. So let yeah. Uh, but before I do this, maybe just one remark, but it will become clear from this also. Okay, suppose I give you a function f of x which is non-negative, um, integrable, non-negative valued integrable function such that the total, that integral ft dt from minus infinity to infinity equals 1, then that's always density function of a random variable. So that is the thing. Maybe, how much time do I have? Oh, I, I will make that remark next time again. Okay. So for now, let us do a very simple, straightforward numerical example. Let f of x be is equal to c divided by square root of x minus 1 minus x, 0 less than x less than 1. Okay. Find c so that fx is the density of a random variable. Okay, it's understood continuous because only for continuous we talk about density. Yeah. Okay, so this is a very simple problem. You know that minus infinity, infinity. Yeah, so wherever it is not defined, it is 0 otherwise. Okay, 0 otherwise. So ft dt, this must be equal to 1. So this is equal to integral 0 to 1 c times dx by square root of x 1 minus x. This is equal to c times integral 0 to 1 dx by square root of, just expand it, x minus x square. But you can express this as a difference of two squares, no? So c integral 1 to infinity. I will not do this completely, but you are good at remembering the formulae. So this is, so so if I add and subtract 1/4, then 1/4 plus x minus x square, that becomes x minus, so x minus 1 by 2x 1 by 2 whole square. So I had subtracted 1 by 4, so I must add 1 by 4, which I write as 1 by 2 square. And this fits into some formula. You can use that formula and complete it. Yeah. I remember the formula for, I mean, I remember the formula for this type of things. Okay. This is sine inverse. Okay. Sine inverse of t. So, but I'm sure I'll make a mistake if there is an a square. I know how to do it, but I will let you do it and compute the value of c. C is equal to what? Okay, compute it. Okay, so one more problem of this nature.
Sir,
Yes.
so one more question in the, like when you were proving the previous thing, sir, like the previous theorem about
Hmm.
joint function. Uh, so could you scroll up? Like above this. Oh yeah, here. Uh, so you showed that you wrote the product, which is uh, below this.
Yeah.
Yeah, the product. The next line you equated it to. You took the integral inside, right? Like The second.
Sorry. So I noticed that there's a typographical error here. So I just change it. Now it will become clear to you. See, this is just a separation of variables. It doesn't really matter, no? ds, dt. So far as doing first integration is concerned, s is like a constant. So you pull it out. So here also I messed up this notation. So this must have been s and ds. You understand this type of error. One should avoid it, but sometimes, yeah. So you understand. See, that's it. This is so far as this. So you evaluate this, you get back this one. You see, because when you do an integration, you do it one thing at a time. If you integrate it with respect to s, so here it should be dt and ds, the way I have written the order. So when you first do dt, so far as t is effects of s, that doesn't involve t. So it's a constant, it comes out. No?
Yes.
That's it. So that's how you get this.
Yes, sir.
Okay. Sorry about these minor typographical errors, but can't avoid it. I'm very poor at this. Okay. Is that clear to you what I said? So you just do it. I mean, when you do it, it's just a double integral. If you have not done multiple integrals yet, uh, this I can spend one lecture doing that. But by now you must have done.
Yes, I understood. Yeah.
Okay. Definitely you must have done integration with respect to polar coordinates r and theta. So it's about the same thing except s and t. Okay. All right. So I have time for one more problem. Very quickly I will do it. This is also given in the book. So maybe B. So f of t is equal to e power minus t minus e power minus t or something like that. dt. Sorry. Yeah, I am always used to writing density along with dt. But okay, so c times. And you need to determine the value of c. Just let me see if I have written that correctly. Oh, sorry. Mm. Yeah, that's correct. Okay, what I have written down is correct. So, uh, yeah, t goes from minus infinity. T is positive, I suppose. 0 less than or equal to, I think 0 less than or equal to t. Didn't pay attention. T is arbitrary. Okay. T is arbitrary. T is in real numbers. Okay. So you have to do this minus infinity to infinity. There's only one way to compute the thing. So 1 is equal to c times this. Okay, e power minus t power minus. So there's a minus also. E power minus t dt. So this you can rewrite it as integral c times minus infinity e power minus t times e power minus of e power minus t dt. And the obvious substitution is put e power minus t is equal to u. And now complete the problem. So you'll get some nice value for c. Complete it. So e power minus t dt minus of this is equal to du. So this and this has become du, and then this can be rewritten as c times integral. Okay, you have to write the limits carefully, but this has now become e power minus u du, which is very easy to integrate. And now you have to wonder, as t goes from minus infinity to plus infinity, what happens to u? So just this becomes, as t goes to plus infinity, it becomes uh, t goes to plus infinity, this becomes 0. t goes to minus infinity, this becomes infinity. So it is like this. Now you complete it. Now you complete and find the value of c, and I'll stop here for today. We will work out more problems next lecture. Okay, that's all for today.
Thank you, sir.
You're welcome.